If you think modern engineering represents the absolute pinnacle of construction, I'm about to ruin your confidence in under 30 seconds. Right now, in Baalbek, Lebanon, 3 massive stone blocks sit fitted inside a temple wall. Each block weighs approximately 800 tons. To put that into perspective, 800 tons is the equivalent of 2 fully loaded Boeing 747s. Today, if we want to lift something that heavy on a construction site, we need months of preparation, heavy counterweight tracked cranes, and reinforced ground pads just so the machinery doesn't sink into the dirt. Yet thousands of years ago, a culture without diesel engines, hydraulic pumps, or steel cables moved these stones, lifted them over 20 feet into the air, and fitted them together so tightly that you cannot slide a single sheet of paper between the joints. Official history tells us this was accomplished using wooden rollers, hemp ropes, and thousands of enslaved workers pushing in unison. But if you actually sit down and calculate the physics, that mainstream explanation completely falls apart. Hemp rope under that amount of tension snaps long before the stone even twitches. Friction against the ground would crush wooden rollers into sawdust almost instantly. So, we are left with a brutal, logical contradiction. Either our ancestors possessed physical abilities that violate basic mechanics, or they knew something about manipulating mass and material that we simply haven't rediscovered yet. Today, we are going to look strictly at the physical evidence, the tool marks, the weight calculations, and the precise geometric cuts to answer one simple question. How did they actually build this? Let's start by looking at the core problem of tool technology. When mainstream archaeologists explain ancient construction, they constantly point to copper chisels, stone hammers, and wet sand abrasives. And on soft limestone, sure, a copper blade can make a dent if you have enough time and patience. But the moment you move from limestone to igneous rock like rose granite or basalt, the copper chisel theory becomes physically impossible. Granite has a Mohs hardness scale rating of 6 to 7. Copper sits at roughly 3. Basic material science dictates that a softer material cannot cut a harder material without suffering total deformation instantly. If you hit granite with a copper chisel, the chisel flattens. The granite barely notices. Yet inside the Great Pyramid of Giza, in the King's Chamber, we find massive granite beams weighing up to 50 tons each, transported from quarries in Aswan over 500 miles away. But the distance isn't even the most confusing part. It's the cut marks. When engineers examine the sarcophagus inside that chamber under industrial magnifiers, they don't see hand-chipped surfaces. They see feed lines. Circular saw marks with a downward feed rate that exceeds what our modern diamond-tipped drills can achieve under high pressure today. A handsaw moving back and forth leaves uneven, shallow grooves. High-speed mechanical circular blades leave deep, uniform, spiral grooves. The core samples extracted from these stones display a feed rate into granite of roughly 1/1000th of an inch per revolution. That requires tremendous downward force, tons of pressure per square inch, applied simultaneously with high rotational speed. Now, skeptics often say, given enough time and human labor, anything is possible. But this argument completely ignores the math of efficiency and accuracy. High precision is not an accident born from random manual labor. Precision requires control. Consider the outer casing stones of the Great Pyramid. Before they were stripped away during the Middle Ages, the pyramid was covered in over 100,000 polished white limestone blocks, each weighing roughly 15 tons. The tolerance between these blocks was average 0.02 inches. That is less than the thickness of a standard credit card. Furthermore, the optical flatness across surfaces measuring tens of square feet stayed within tolerances that modern optics factories reserve for high-grade mirrors. If a worker using a copper tool and a stone hammer makes a mistake of just 2 millimeters on the base layer, that error compounds exponentially as the structure goes higher. By the time you reach the top, the entire pyramid would be twisted and structurally compromised. Yet the base of the Great Pyramid is flat to within less than an inch across a footprint of 13 acres. Think about that footprint. To level 13 acres of natural bedrock today, we use laser transit levels, GPS mapping, and heavy earth-moving bulldozers. If you try to achieve that degree of leveling using water trenches and plumb lines over uneven terrain, the margin for human error is astronomically high. Yet, the physical reality sits right there on the Giza Plateau, perfectly aligned to true north within 4/60ths of a single degree. But Giza is only one piece of a global puzzle. If you fly across the Atlantic Ocean to the high Andes of Peru, you encounter Sacsayhuamán, a megalithic fortress perched over 11,000 feet above sea level. The stones here are not uniform rectangular blocks like Giza. They are massive, multi-angled polyhedral monoliths, some weighing well over 120 tons. Every single stone has custom curved joints, like a three-dimensional jigsaw puzzle made of solid rock. Traditional history claims the Incas built this site using stone hammers to pound the surfaces until they matched. But let's analyze that process practically. To fit a 100-ton irregular stone onto another irregular stone with 0 gaps, you have to lift the top stone, check where it rubs, lift it back off, scrape away the high spots, and lower it down again. You would have to lift and lower a 100-ton rock hundreds of times just to fit one single joint. That is not just inefficient, it is physically absurd on a steep mountain slope with limited workspace. What makes Sacsayhuamán even more fascinating is its seismic resistance. When major earthquakes hit Peru over the last few centuries, modern Spanish colonial buildings collapsed into rubble. The megalithic walls of Sacsayhuamán didn't even crack. During a seismic event, the custom multi-angled joints actually flex and settle back into place, dissipating the kinetic energy throughout the structure. That isn't primitive stonework. That is advanced, highly calculated earthquake engineering integrated directly into stone masonry. If Sacsayhuamán demonstrates master-level structural engineering, Puma Punku in Bolivia takes precision into the realm of manufacturing. Located over 12,000 feet up in the Altiplano, Puma Punku consists of scattered blocks made of red sandstone and diorite. Diorite is one of the hardest rocks on Earth, surpassed mainly by diamond. Yet the blocks at Puma Punku feature perfectly straight internal right angles, uniform drill holes running through solid stone, and long straight channels that look identical to modern CNC milled aluminum. I want you to really visualize this. We are looking at blind holes drilled into dense stone with uniform depth, 0 chatter marks, and equal spacing down to fractions of a millimeter. When modern engineers measure the inner right angles of the famous H-blocks at Puma Punku using precision machinist squares, they find 0 light leakage through the corner. To achieve a perfect 90-degree interior angle in diorite without rounded corners requires an extremely sharp, high-speed cutting bit moving along a fixed mechanical axis. You cannot achieve that by hand with a piece of string and a stone hammer. Hand tools slip. Hand pressure fluctuates. Handwork leaves organic imperfections. What Puma Punku exhibits is standardized, mass-produced modular components. The H-blocks are so identical in their measurements that they appear to have been manufactured off a template or blueprint. So why would a primitive culture spend thousands of hours precision machining diorite blocks with modular interlocks high up in a barren mountain plain where trees don't even grow to provide timber for rollers? That brings us directly to the problem of transportation logistics. Moving heavy mass across natural terrain is entirely governed by friction and load distribution. The standard textbook image shows hundreds of workers dragging a massive stone on a wooden sled across sand or mud. Let's test that theory with actual physics. The coefficient of friction for wood sliding on dry earth is roughly 0.4. If you are trying to pull a 200-ton stone block, the pulling force required just to overcome static friction is 80 tons of force. An average human pulling on a rope can exert roughly 50 to 60 pounds of sustained force without collapsing. Do the math. You would need over 3,000 people pulling simultaneously on a single rope network. Where do 3,000 people stand? How do they pull in unison without stepping on each other on narrow mountain tracks? Furthermore, the tensile strength of natural fiber rope, even thick braided hemp, caps out at a specific load threshold. If 3,000 people apply 80 tons of force, the main haul line snaps violently before the stone moves an inch. At sites like Ollantaytambo in Peru, the quarry sits on one side of a mountain valley, and the fortress sits on the opposite ridge. To get the stones there, the builders had to bring 50-ton blocks down a steep mountain slope, across a rushing river, and up an equally steep cliff face. Gravity works against you in both directions. One slip, and a 50-ton stone accelerates down the slope, crushing everything in its path. That requires braking systems, mechanical advantage, and load management that go far beyond simple human muscle. Whenever these physical contradictions are raised, the immediate counterargument from conventional historians is, if an advanced technology existed, where are the machines? That is a fair logical question. Why don't we find steel drills, iron crane parts, or engines buried in the archaeological layers? But that question assumes a very narrow view of technological development. We assume that any advanced civilization must follow our exact industrial path, burning fossil fuels, casting iron, and forging steel. But history shows us that technical knowledge can vanish completely when a civilization collapses, leaving almost no physical trace of its methods. Take Roman concrete, for example. For nearly 1,500 years after the fall of Rome, no culture on Earth knew how to make concrete that could set underwater and grow stronger over time. The recipe was lost, and for centuries, people looked at Roman harbors and wondered how they built them. It was only recently that modern material scientists discovered the specific chemical reaction between volcanic ash and seawater. Look at the Antikythera mechanism, a complex, gear-driven analog computer built by the Greeks in the 2nd century BC, used to predict astronomical positions. Nothing like it appeared again in human history for over 1,000 years, until mechanical clocks emerged in Renaissance Europe. If the ship carrying the Antikythera mechanism hadn't sunk into protective silt, we would have zero physical proof that the ancient Greeks possessed complex differential gearing technology. Technological knowledge is remarkably fragile. So, if we look at the physical evidence objectively, what are the leading scientific theories that actually account for these anomalies without resorting to wild speculation? The first serious scientific hypothesis involves geopolymer chemistry. Proposed by materials scientist Dr. Joseph Davidovits, this theory suggests that some megalithic blocks, specifically at sites like Giza and South America, were not carved at all, but poured like modern concrete using reconstituted limestone or granite slurry. If you dissolve limestone using natural chemicals like lime and soda ash, mix it with binding minerals, and pour it into wooden molds, it hardens into solid rock that is chemically almost indistinguishable from natural stone. This completely solves the transport problem, the tight joints, and the precision angles. You don't drag a 100-ton stone up a mountain. You carry small buckets of wet slurry and pour it in place. However, while this theory explains certain limestone blocks exceptionally well, thin-section petrographic analysis of many granite and diorite megaliths shows natural crystal structures, quartz veins, and grain alignments that could only form under deep geological pressure over millions of years. That means those blocks were definitely quarried from solid bedrock. The second major hypothesis centers on high-frequency sound wave resonance and mechanical vibration. We know that sonic drilling uses ultrasonic vibrations to allow soft copper tools to rapidly cut through extremely hard materials by shattering the rock at a microscopic level. Could the ancients have mastered basic acoustic mechanics? What makes the acoustic and resonance theory so compelling to researchers is that acoustic properties are intentionally engineered into many of these ancient sites. At the Hypogeum of Hal Saflieni in Malta, a subterranean stone temple built over 5,000 years ago, there is a specific chamber known as the Oracle Room. When a male voice chants at a frequency of precisely 110 Hz, the entire underground complex resonates, creating a standing sound wave that vibrates through the solid stone walls. Neuroscientists testing this room observed that 110 Hz matches the exact resonant frequency that alters human brainwave activity, shifting cognitive processing into the prefrontal cortex. That is not a random coincidence. That is acoustic design built directly into underground architecture. We see similar acoustic phenomena in the Grand Gallery of the Great Pyramid, in the ancient stone structures of Ireland, and in Mayan pyramids like Chichen Itza, where a sharp clap produces an echo that perfectly mimics the call of a bird. Why were totally isolated cultures across different continents obsessed with tuning massive stone structures to specific sound frequencies? Were they simply creating ritual acoustic spaces? Or did they understand a fundamental relationship between acoustic frequency, vibration, and the physical properties of matter that we are only beginning to re-explore today in modern physics labs? When you step back and look at all these sites collectively, Baalbek, Giza, Sacsayhuamán, Puma Punku, a clear global pattern emerges. We are not looking at isolated incidents of random primitive genius. We are looking at the surviving remnants of a global engineering paradigm that operated on principles completely different from our current industrial civilization, where we rely on brute force, combustion engines, and massive energy expenditure. They may have relied on precise geometry, material chemistry, natural frequencies, and subtle mechanical advantage. They worked with the inherent physics of the Earth rather than trying to force their way through it. To look at these silent, massive stone monuments and dismiss them as simple products of primitive manual labor, ropes, and wooden sticks is not just an insult to our ancestors' intelligence, it is bad science. It ignores the tool marks under our microscopes, ignores the friction math, and ignores the precise astronomical alignments baked into solid rock. The true history of human technological development isn't a simple, straight line pointing upward from primitive monkey men to modern smartphone users. It is a complex cycle of peaks, catastrophes, lost knowledge, and slow rediscovery. The physical evidence stands right there in solid granite, waiting for us to ask the right technical questions instead of accepting comfortable historical narratives. What do you think? Did our ancestors possess forgotten technological methods, or are we severely underestimating human muscle power? Drop your thoughts in the comments below. Let's debate the facts logically. If you appreciate deep, evidence-based historical analysis, hit the subscribe button and turn on notifications. Thanks for watching, and I'll see you in the next deep dive.